Hi guys, today I want to discuss Gaskell 9.3 question. So in the 9.3 question, we are given excess Gibbs free energy and we are asked to find whether it's a regular solution. So regular solution is a form of this. So the delta H mix is nothing but delta G excess. Now we need to find delta G mix total and few other things. So given information is the table. And for a regular solution, delta H mix equals to omega xb. So it's a parabolic type solution. An ideal solution, the delta H mix is 0. So it's perfect mixing. So for the delta G mix, the formula is delta H mix minus T delta S mix. So we need to find the delta H mix. So let's assume it's a regular solution. And it is a parabolic type equation. So let's calculate omega based on the table. So it's nothing but delta H mix minus by divided by XA into 1 minus XA. So that is nothing but delta G mix XS by XA into 1 minus XA. So we have given two things. So I'll start with 0.1 and 0.2. So omega at 0.1 is nothing but 4389 and omega at 0.2 is 4393.75. So let's write the table in Excel and compute the omega for each composition. So now I'll calculate for each composition and I'll take the average of all these omegas. So I have an average of 4395 with standard deviation 6.27. So they are near 4,395. Hence the average omega is 4395 with a plus or minus 6. So we can assume it's less than 0.1% difference standard deviation. So we can say that it's a regular solution. Now the delta G mix, we know the equation. So we will just expand this equation so that we can get a clarity. So the delta S mix is the configurational entropy. As you know, configuration entropy is R summation xi ln xi. So after expansion, I get a formula looks of this form. Now I have the partial molar property of one component is given by this formula. You can find in any Gaskell textbook. So let's focus on this equation. So I'll find the component is partial molar property. So I'll put delta G mix here and differentiate with respect to one component. So when I differentiate omega xa xb, I get 1 minus 2xa. Now I differentiate xa ln xa and xb ln xb. So I expand xb in terms of xa, 1 minus xa. So I get 1 plus, it's ln xa first and then I differentiate ln xa, I get xa by xa. In a similar fashion, I get minus 1 into ln 1 minus xa and I get 1 minus xa by 1 minus xa. So it boils down to very simple formula. So plus 1 minus 1 cancels. So I multiply this to get something of this form. Now I expand my delta G mix. After making a very clear expansion. So I write down the formula of delta G mix. And I write down the other part. So I can cancel few terms here because there is subtraction. So I cancel omega xxb and I cancel the configuration entry part. So I have left with two terms. So those two terms is omega xb square plus RT ln xa. So this is for the A component partial molar Gibbs free energy of component A. So this partial molar Gibbs free energy is nothing but chemical potential of A. Similarly, we can get the partial Gibbs free energy of B. So it's a very simple equations. Now we have to know that this term is the excess part and this term is from the ideal part. Hence, the delta GA excess is nothing but omega xb square. So A component is iron and B component is manganese, and given the mole fractions of each component, and after multiplying we get the delta GA excess and delta GB excess in terms of joules. Now for the C part we need to find the delta G mix. So you already know the delta G mix term. So that is a very simple substitution of the values into the equation, and finally you get minus 9370 joules. So let's go to the appendix A, table 8.4 on the back of the Gaskell textbook. From there you can get the standard vapor pressure of iron and manganese, which has this form. We will use this appendix part in solving our D part. So we know activity is nothing but the partial property of the pressure of I, that component I, divided by the partial standard pressure. So we can find this partial standard pressure at a particular temperature using the formula we obtained from the appendix A. So we get for each component the standard vapor pressure in terms of atmospheres. Now we use the delta G, that is the chemical potential, which is nothing but RT ln of activity of component A. So we can get ln of A equals to, we substitute the values at 0.2 iron and 0.8 manganese mole fraction, and we get the activity by taking the exponent of this value, and in the similar way we do the same thing. So the pressure of iron component at this particular temperature is given as 3.68 in 10 power minus 5 atmospheres, and manganese you will get a better pressure. Thank you for watching this video. If you like the content, please click on the like button and subscribe to our channel. Also, if you have any comments, please do comment below. and help us to make better content.